Good morning, everyone. My name is L. Sriram Kumar, and I'm a cosmologist working here at the Indian Institute of Technology, Madras. As you may have noticed, the scientific organizing committee for the school consists of Professor Guillaume Fay from the Institute of Astrophysics, Paris, Professor B.S. Satyaprakash from Penn State University and Cardiff University, Professors Dawood Kotawala, Chandrakant Mishra, and myself from IIT Madras. On behalf of the Scientific Organizing Committee, it gives me great pleasure in welcoming you all to the school. The school is being held by the newly instituted Center for Strings, Gravitation and Cosmology at IIT Madras. Let me say a few words about the center and the school before I go on to introduce Professor Sanjeev Dhurandhar, the first lecturer at the school. During the last year or so, IIT Madras was identified as one of the institutes of eminence in India. As an IOE or Institute of Eminence, our institute has recently created centers of excellence, one of which is the Center for Strings, Gravitation and Cosmology. Apart from me, the faculty at IIT Madras who are members of the center and the research interests are Professor Suresh Govindarajan and Ayan Mukhopadhyay with interests in string theory and aspects of black hole physics, Professor Dawood Kotawala, who is interested in classical and quantum gravity, and Professor Chandrakant Mishra, who has interest in gravitational waves. I would like to mention here that we have also formed an advisory committee consisting of Professor B.S. Satyaprakash, one of the members of the SOC for the school, Professor Jerome Martin of the Institute of Astrophysics, Paris, and Professor Kostas Skendris from the University of Southampton to guide us with the plans for the center. Being a theoretical group, the primary goal of our center is to increase academic interactions and collaborations. Apart from having regular national and international visitors, we expect to conduct lectures, schools, and workshops every year on different topics of our interest. For instance, we have initiated a new lecture series in honor of Professor Subramaniam Chandrasekhar, and in fact, the second lecture in the series will be given later today by Professor Clifford Will. Also, I should mention that in a couple of weeks, during February 2 to 5, we'll be holding the second Chennai Symposium on Gravitation and Cosmology. Let me now say a few words about the school. The school is intended to introduce graduate students and postdoctoral fellows to research themes of current interest and in black hole physics and gravitational waves. We have a wonderful set of lecturers for the school. We have Professor Sanjeev Dhurandhar lecturing on basics of gravitational waves, Professor Eric Gurgulhorn lecturing on black hole physics, Professor Paolo Pani speaking on tests of general relativity, Professors Badri Krishnan and Eric Poisson who will be lecturing on theoretical aspects of black holes, and Professor Monica Kolpi speaking on observational aspects of black holes, focusing in particular on the astrophysical implications. Note that these lectures will be complemented by tutorial sessions that will provide hands-on experience to the participants. Now, let me say a few words about Professor Sanjeev Dhurandhar, who will be giving the first lecture at the school. I'm very glad to hear Professor Dhurandhar. Professor Dhurandhar is an emeritus professor at the Inter-University Center for Astronomy and Astrophysics, Pune. Since 1989, he has been extensively involved in extracting optimally the gravitational wave signals from noise. He has made foundational contributions to the analysis of gravitational wave data. He has proposed several techniques that lie at the heart of modern search algorithms, such as the stationary phase method. I should also mention here that he is one of the proposers of the LEGO India project for the construction of a gravitational wave observatory in India. Professor Dhurandhar has won many awards, including the Vigyan Bhushan Firodia Award in 2016, the ABP Maja and the TMC Pune Gaurav Awards in 2017, the Meghnad Saha Memorial Gold Medal in 2018. I should also add that in 2016, he had also shared the Milner's Special Breakthrough Prize for Fundamental Science with the LEGO Scientific Collaboration. Professor Dhurandhar is a fellow of all the 3 Indian Science Academies and also a fellow of the American Physical Society. I will now request Professor Sanjeev Dhurandhar to give the first lecture on the basics of gravitational waves. Over to you, Sanjeev.
Thank you, Sriram. I'm very happy that I've been invited to be one of the lecturers to the school, and I thank the organizers and the organization committee and of IIT Madras Physics Department and this new center which has started. I am very happy that this will uh, that this center will arrange a lot of things, a lot of programs, events which will foster astronomy and astrophysics, especially things like black holes and gravitational waves and cosmology. So this is the Center for Strings, Gravitation and Cosmology, and we hope that it will, we expect that it will do a lot of things from now. So should I share the slides now? So what should I?
Sanjeev, please go ahead. Yeah.
So, what do I do? Okay.
At the bottom, you say shares. There is a share screen, right?
Yeah. So there, share. Okay. 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 So this is the. So when I was approached for these lectures on gravitational waves, I was. They were supposed to be on basics of gravitational waves, and this is exactly what I've done. So if you find these lectures a bit too elementary, then I could have pitched my lectures at any level, but I thought that this is what the organizers wanted, that I should start from the beginning. So these are basically introductory lectures, and they are more pedagogical, and so if you already know many of these things, then I mean, you're free not to attend, or you can. There might be a few things which may be of interest also in these things. So you know what I say here. So first, in this first part of the lecture and all that, I'll talk about Einstein's equations, give a quick recap of Einstein's equations, what they are about, and so on. This is absolutely for the beginners, and so that is what I'm going to do. And then I'm going to go on to gravitational waves and the linearized theory. Okay, so that will be basically my first lecture, which I'll be giving here today. So, so the first thing is Einstein's equations. So, what are the Einstein's equations? So, these are the Einstein's equations. I mean, if you know, if you see the history and so on, there was a Newton's theory of gravity, but Newton's theory of gravity ruled for about 250 years since Newton gave it, until Einstein came, and he gave this special theory of relativity. In fact, all that was done because of electromagnetism. Electromagnetism and so on obeyed a certain, they were covariant under the Lorentz transformations rather than the Galilean transformations. So, but so there was so Einstein, in fact, turned the things around and gave his special theory of relativity. But special theory of relativity simply did not, and Newton's theory of gravity, they simply were inconsistent. And it is impossible, or it is unacceptable to have two theories which are inconsistent with each other in physics or in any science for that matter. And so Einstein, 1915, gave his general theory of relativity, and this is where I'll start. So Einstein's equations are here. So what do the Einstein's equations say? They relate curvature to matter. So on the right hand side, on the left hand side, we have curvature. That curvature is a manifestation of gravitation. So gravitation is a manifestation of curvature of space-time. So if you have matter on the right hand side, then this is how the Einstein's equations relate the curvature to matter. Of course, you can have even curvature without matter. And we can put the things to be zero on the right hand side, but still you will get curvature and so on. So there are solutions like that also. So this is so you have curvature relates to the matter distribution. The matter distribution is described in terms of what is called the energy momentum tensor, and that is on the right hand side. G and C are the fundamental constants. G is the gravitation constant, Newton's gravitational constant, which is 6.67 into 10 to the minus 8 in CGS units, and C is 3 into 10 to the 10 centimeters per second. So these are the kind of things. T mu nu usually, as is written here in this particular equation, T mu nu has dimensions of pressure. So it is force per unit area. Okay. So this is what this particular equation is. So let's go ahead and see what this is. So let me try to explain what is on the left hand side of this thing. What is curvature? So many times I found that students also, I mean, when they come for MSc and so on, they do not have, I mean, they do not know of any other geometry other than the Euclidean usually. And so it's not very clear to them what's going on. And many other people, students who are there also there, who have done the differential geometry at the high level. Okay, we're using differential forms and differential manifolds and so on. They also do not have too much idea what they are talking about, although they may be able to work with or may be able to throw out those such terms. So here's curvature. So let's talk of curvature just in 2 dimensions. So here's curvature in 2D. So what is curvature? So you can, the indication of curvature, an object which is of the simplest kind of object that we know which is curved is the sphere. It's a very symmetric object, so that's why it's a very simple object. And on this sphere, if you draw a triangle, okay, a triangle is made up of 3 points. This is ABC, and there are 3 curves which join this. These curves are geodesics. Geodesics means they are the straightest possible curves that you can draw on the surface of the sphere. They are in fact the great circles. So if you draw these great circles, join ABC by the great circles, you get a triangle. Now you can even see there that if you take A and B on the equator, C say 90 degrees away on the equator, the 3 angles will not add up to 90 degrees, 180 degrees. They'll add up to 270 in fact, or they'll add, in any case, any triangle if you take here, they'll add up to more than 180 degrees. And the point is they do not add up to 180 degrees. So the sphere is simply, this is one of the theorems of Euclidean geometry, that the 3...
Sanjeev, this is Sriram. I'm sorry to interrupt. There is a request to see whether you can make your thing full screen. Will it be possible to do that?
Full screen.
Yeah. Just go to the that horizontal band of lines. If you click, there should be make it present as slideshow. Is that okay?
Where is the full screen?
Yeah, make it present as slideshow.
What?
Above that. No, below, present as slideshow.
Just slideshow. Oh, it doesn't say anything like that.
Here, below save as, I can see it right in that column. There it is.
Okay. Great. Okay, good. Okay, so yeah, okay. So here's the sphere. Yeah. So the angle, so the point I was making was the 3 angles of the triangles do not add up to 180 degrees. So what this means is that we are dealing with some object which is not Euclidean. Because you know that for a Euclidean space, like a plane or something, then if you draw a triangle, the angles always add up to 180 degrees. In fact, That is also sometimes stated as one of the axioms of Euclid. Okay, I mean you can you can switch the axioms this way, that way. So here it doesn't happen. So that means that you're dealing with a non-Euclidean object. Now you ask the next question. How non-Euclidean? How much is it non-Euclidean? Can you measure the non-Euclideity? So then you measure the discrepancy. It is, you write A plus B plus C as pi plus delta. Pi is 180 degrees plus delta. And then this delta gets related to the curvature. Delta is equal to integral K ds, where K is called the Gaussian curvature of the surface. And for the sphere, it is just 1 over r square. There's a formula down there, which is given as product of the two principal normal curvatures, kappa 1 and kappa 2. It is equal to 1 over the principal radii of curvature of the surface, r1 and r2. The sphere being such a symmetric object, r1 is equal to r2, equal to the radius of the sphere. So k is 1 over r square. So this is the Gaussian curvature. In fact, this is a statement or a particular case of what is called the Gauss-Bonnet theorem for geodesic triangles. Perhaps I think some of the lecturers might refer to some things like this, Gauss-Bonnet terms and things like that. I don't know. So it might be, so maybe this part of the thing could be relevant there also when people are talking about black holes or something like that. So K here is the Gauss-Bonnet. So just one more comment about the Gauss-Bonnet theorem. Gauss-Bonnet theorem relates geometry to topology. In fact, there is this thing between the geometry and topology, and it is actually given related to the Euler characteristic, which is given by chi equal to E minus B plus F. So if you take any kind of a surface or something like that, and then take its edges and the vertices and the faces and do this calculation, it gives you what is called the Euler characteristic. In case of the triangle, for example, here you have three vertices, 3 edges here, and 1 face. So chi is 1 in this case. And so you can apply that and all that sort of thing. Then carry out the things, how much you turn by the angles. I left out a term here. It is actually integral of kg ds, which is the geodesic curvature of the curve. Okay. In this case, the geodesic curvature is 0 here because we have taken geodesics. But at the turning points ABC, you have to add that term. So there are the external angles, and you will find that this is exactly that. But for the sphere, for example, the Euler characteristic is, I believe, 2. Okay. So that is the kind of thing. And then you get this whole thing is 4 pi. Okay, k over r square ds is 4 pi. So it should be, so one can do that. Anyway, this is not relevant to gravitational waves. What is relevant here is I am talking about, but it may be relevant for other lectures. That's why I thought I'll make a digression here. Okay. So now I go on to the next thing. So delta, one thing one must see as can have either side. So I have shown the sphere, but there are also things like the hyperboloid. So if you look at this hyperboloid, it is something of negative curvature. If you draw a similar triangle here, ABC here, then the angles add up to less than 180 degrees. Okay. So then this delta is negative. And delta can only be negative if this k is somewhere negative. At least it has got negative things. So delta can have either sign. For the sphere, k is greater than 0. For the hyperboloid, on the other hand, k is less than 0. And why it is less than 0? If you take the normal curvature if you try to measure the k, say at the center point of this hyperboloid, one circle will lie inside, one circle will lie outside. So there are 2 different signs. You can give different signs to the principal radii curvature. So k becomes negative. So in 2D, so we have k greater than 0, k less than 0. And this is important for gravitational waves because we are now going to see that we are going to talk of oscillating Riemann tensor. And when you are talking of oscillating Riemann tensor, the curvature keeps changing sign. So you will always have positive and negative curvature. So that's why I thought I will show you this k greater than 0 and k less than 0. These are also realized as figures embedded in three-dimensional Euclidean geometry. Now, in 2D, you had only one such thing. In n greater than 2, that's a more complex situation. So this is what is called a two-dimensional manifold, what we are talking of, the sphere and the hyperboloid. There are two dimensions because only two coordinates are required at any point to specify a point. So those are called actually coordinate patches. I am not going to get into the whole geometry of different or whole things of differential manifolds, but those are called charts and so on. So these charts have just any chart will have just two coordinates. So these are just two-dimensional objects. In 2D, just one function. So the point here I'm trying to make is that in 2D, just one function is required, k, to describe the curvature. But as you increase the dimensions, n becomes greater than 2, a more complex object is required. And therefore, because you can take slices as you like in higher dimensions. As you go to higher dimensions, you require, it's a more complex thing. So more complex object is required and therefore several functions. And that particular object is the Riemann tensor, R, mu, nu, lambda, sigma. So this is a very much more complicated object. It has, it's a tensor, fourth rank tensor. Therefore, in 2 dimensions, for example, it will have 16 components, but they are not independent. Most of them are 0 because of the symmetries. There's only one independent component, R1212, and divided by G or something, the determinant of the metric. But anyway, so only one independent component is there in 2D. If you go to higher number of dimensions, in 4 dimensions, as we will be dealing with, we require 20 of them. In 3 dimensions, you will require 6 of them. So there's a formula for that. And physically, in general relativity, this object, Riemann tensor, actually describes tidal accelerations or forces. So curvature and metric. So what you do is we have a Riemannian manifold, differential manifold. So the model for general relativity is a Riemannian manifold, differentiable manifold, which I am not going to define, except that it's a manifold with a metric. It's a differential manifold with a metric. You are given a metric, G alpha beta. And the Riemann tensor is connected to this metric. In fact, once you give the metric, in fact, this was one of the things of Gauss, that once you give the metric and the thing, you have basically specified everything that you know about this. He was doing things about surfaces. So once you give, say, the chart and the metric, that's it. You can calculate anything else, say the Gaussian curvature. It just turns out to be a very complicated function of this metric functions. So the Riemann tensor is a very complicated function of the metric. Its first and second derivative, I have written it out there. So Riemann tensor is given in terms of the gamma symbols or the Christoffel symbols. So these are the Christoffel symbols which are there. Christoffel symbols are given in terms of the metric, and the metric is written down there. So G alpha delta, which contravariant as it's called, is also a tensor, contravariant tensor of the second rank. And gammas are basically derivatives, first derivatives of the metric. And first derivative of the metric will then correspond to something like accelerations due to gravity. The G, in fact, plays the role of a potential. I mean, if you want to connect. Finally, Einstein's theory in the weak field slow motion limit has to go over to Newton's theory. After all, Newton's theory was there for 250 years. It explained so many things. So, in its limited region of validity, you must always, I mean, Einstein's theory has to go over to Newton's theory. So, when you make these correspondences, the metric, in fact, is like a potential. Like gammas are like the accelerations or acceleration due to gravity, and the Riemann tensor are the tidal forces. Okay, so now I come to the RHS. The RHS is the matter distribution. Okay, the RHS is the tidal. So if you go back here, where is it? Okay, now here you have this tensor T mu nu, which is coming there. The right hand side describes the matter energy distribution. Now, so in case of Einstein equations, the gravity is not just created by the density of matter. In case of Newton's theory, it was just rho, del squared phi equal to 4 pi g rho. Here we have a whole tensor T alpha beta, which connects the left hand side, which is the curvature. So what I would like to, I probably missed that step here, or yeah, these, so I forgot to define R mu nu and R. They are contractions of the Riemann tensor. If you contract the Riemann tensor, the first and third, that's one of the conventions, alpha and gamma, to get the Ricci tensor. So you'll get R beta delta. All these things probably you'll see in the tutorial, so you don't have to, I mean, you'll go over it again, those who are absolutely new to this field. And R is the scalar curvature, which is again another contraction, so which is a G beta delta on R of beta delta. Or you can contract R, see, look at the first line, R alpha beta gamma delta. R alpha beta alpha delta will be R beta delta, that is the Ricci tensor. Now, if you contract that with G beta delta, you will get R, the scalar curvature. And what you make out of the scalar curvature and the Ricci tensor is this Einstein tensor, as it's called. It's R mu nu minus half R G mu nu. So that gives you the left hand side of Einstein's equations. So why is it made like this? But why is it like this? I mean, why haven't you taken just Riemann tensor or Ricci tensor and put that equal to 0 or something? So the reason why this is there is it implies conservation law. There is the so-called Bianchi identities. So R mu nu minus this Einstein tensor has a vanishing divergence, which matches with the conservation laws because T mu nu also has a vanishing divergence, and which implies conservation of energy and momentum. So everything is quite consistent in this thing. And so you have this energy momentum tensor, T alpha beta. So what is this T alpha beta? So I just give you a quick this thing on that. T00 is simply the energy density, rho c square. So in case of Newton's theory, it was just rho, okay? But here you have a rho c square. So it is the energy density that has come into the picture. And in this, rho is basically not a scalar here. As you can see, it is a component of a tensor, second rank tensor. So somebody is moving with respect to the matter, will see a different rho, okay? Or a star which is rotating, for example. There the matter will be rotating. So you can't take the rho which is there. You'll have to consider the rho in your frame and the frame which is moving. So you have to connect that with the Lorentz transformation or whatever. And you'll have to apply two of those Lorentz transformations if you want to get rho here, because it's component of a tensor. Then the next thing is the 0k. So k here, so when I'm taking this, so throughout this lectures, this Latin indices will denote the space indices. Okay, I mean, have I already told you about the signature and all that? Maybe not here. Maybe later on I will talk of the signature, or what signature I'm going to adopt for my lectures. So it's going to be minus plus plus plus. Okay, because it is good for, because most of the time we are dealing with the space indices. So the space indices are k going from, so k, in fact, Latin indices will go from 1 to 3, while the Greek indices run from 0 to 3. So there are 4 of them, 0, 1, 2, 3. 0 represents the time, and so or c times t. So there's a c there, and so don't forget the c, because many times, at least in the beginning, it is good to have a crutch like the c, and because I have found that many times students get sort of, I mean, they have questions, and sometimes very good questions. And the reason is that many times people put c equal to 1, and then people, so I mean, students can lose, or people can lose some perspective. Because the speed of light is so large as compared to the normal speeds in our everyday life, that it's just important to keep it there. So many times people say, I mean, I'll come to the next slide and I'll tell you what typical questions one gets from students, and we are very good students actually. And so anyway, if I came to C, so C into T0K is the energy flux across the xk equal to constant surface. So that is C T0K. What is TKK? It is the pressure on the xk equal to constant surface. And in general, TJK is the flux of the jth component of the momentum in the kth direction. It represents special stresses. And C inverse TK0 is the kth component of the momentum density. But there's a symmetry. You can see that it should be there. The TK0 should be equal to T0K. Then how is this? This is energy flux across the x equal to k, xk equal to constant surface, while here it is the kth component of the momentum density. But momentum, as you know, is simply the mass times the velocity. So the mass and energy are same, basically a factor of c square. We can see that there's c multiplying there, here it is c inverse. So there is no this thing here at all. So C inverse TK0 is the component of the momentum density. So these are all the components of the energy momentum tensor, and they relate to the curvature which is given here. They are equal to this curvature. And these are equations now. These are equations for G mu nu, which you need to solve. Because here you can see this. These are second order differential equations. So now next slide is that. Einstein's versus Newton's gravity. Einstein's theory is this, and field equations. R mu nu minus half R G mu nu equal to 8 pi G by C4 T mu nu. And Newton's equation is just one equation. Del squared phi equal to 4 by 0. Okay. So the inverse square law can be put in, the Newton's theory also can be written as a field theory for phi, potential phi. And you solve this with some boundary conditions. For example, the phi goes to 0 at infinity for a point mass, for example. And then you get phi equal to minus gm or r or something like that. Here, Also one does similar thing here to solve these equations with boundary conditions. Okay. So these are in fact horribly complicated equations. Look, this was just one linear partial differential equations. There's one here. It's just phi is just one function which is there, and it's linear. And outside matter it is dealt with Laplace's equation. Okay, and one knows how to solve this sort of equations. But that's not the case here. Here these are coupled partial nonlinear differential equations for 10 G alpha beta. There are 10 of this G alpha beta because you are in 4 dimensions. G alpha beta, if you get the tensor, you can think of it as a matrix, which is a symmetric matrix. Then it has 10 independent components. So there are 10 equations for 10 G alpha betas. Of course, again, they are not independent because of the fact that there are the equations are not independent because of the Bianchi identities. But that is compensated by the fact that the coordinates provide a gauge freedom. So there is a gauge freedom is there because the coordinates you can choose. There are 4 degrees of freedom in choosing the coordinates. X, there are 4 coordinates, x alpha say, and G alpha beta can be given in any of them. And it is the same G alpha beta that we regard. So in this case, so that way the number of equations is actually 6. And the number of G alpha beta also independent ones would be also 6. So these are coupled partial nonlinear differential equations. Even whatever that may be, they are still quite complicated. And because they are nonlinear, you can't superpose solutions, which you could do very well with Newton's or even in Maxwell's theory. You can superpose the solutions of one charge and one charge distribution with another in Maxwell's theory. Just add if you have a rho 1 and say J1, where rho and J are the currents, say, and you get E1 and B1 are the fields, electromagnetic fields that you get out of it. And you have another set of charges, which are rho 2 and J2, which are the charge, what are the charge and the current, and you get electromagnetic fields E2 and B2. And if you superpose these charges where you have put the rho 1 and rho 2 together, J1 and J2 together, then what you ask, what is the field of this thing? You just add the 2 together and you are through. E1 plus E2, B1 plus B2. You can't do that here. If you have one solution for one Schwarzschild solution for mass M1, you can't put another mass next to it and say you have another Schwarzschild solution for M2. So add the G alpha betas together. That will not be a solution to Einstein's equation or for this particular system. And that is the problem. You don't have a binary solution at all for a binary 2 point masses going around together. There is no, so far, after 100 years, there is no analytic solution so far. Okay, nobody has given a solution like that. One has to resort to all sorts of things, post-Newtonian corrections, all sorts of approximation methods, numerical methods in order to solve this. So they are really complicated equations, and so one has to bear that in mind. So I just wanted to point that out to you. So mathematically, these are very complicated equations, and they are hard to solve. And the dynamical variables here are G alpha beta and the Riemann tensor, the metric or the Riemann tensor. Just like in electromagnetic fields, it was the E and B, or you could have the potentials phi and A. In Newton's theory, you can regard phi or acceleration due to gravity as the dynamical variables. So these are the kind of things which are there. And here is a picture which shows sort of a schematic or a cartoon, which shows here. Sometimes, so this is the thing. And in case of Newton's theory, here is a planet, or maybe the Earth, if you like, going around the sun. So this has to be explained by both theories, because Newton's theory explains this by saying that the sun attracts the earth with the inverse square law. F equal to minus gm m1 m2 over r squared, or r cap over r square, and so on. Or you can calculate, solve this Laplace equation, get the phi is minus gm over r and so on, and get the field, and then use Newton's second law to calculate the orbit. And then what you get is an ellipse. Okay, so you get an ellipse which for the path of the earth going around the sun. So that's the picture there. The picture is there that the sun attracts the earth and the earth moves according to Newton's second law. In Einstein's theory, the picture is different. Here you have the sun which curves the space-time around it. How does it curve? Because of the Einstein's equations. You use the Einstein's equations for the sun. Sun sitting at the center, considered to be spherical if you like. Solve the Einstein's equations outside the sun. So the T mu nu will be 0. You can look at it as a Schwarzschild solution. And then from that, you calculate. And what about the test masses like the Earth? They move along the along geodesics, along this particular in this particular space-time. So what happens? The sun creates a particular space-time. The space-time is given by this kind of thing. R mu nu. There it will be R mu nu equal to 0. This is outside the sun. If you put T mu nu equal to 0, then you get 0 on the right hand side. You can take the trace of this. The trace will give you that the scalar curvature also is 0. So R mu nu is 0. So the Ricci tensor, it is a Ricci flat solution. It's called a Ricci flat solution. So what you get is the Schwarzschild solution. And in this Schwarzschild solution, you calculate the geodesic, a time-like geodesic as it's called, of the Earth, of whatever particle, test particle, moving in this particular orbit. So here is the picture here is different. That you have a space-time which is curved, and the curve, and that is the part of the Einstein's thing, that any mass curves the space-time around it, and the test particle or the Earth, for example, moves in the straightest possible path it can in this curved geometry. Now, so this is like, for example, if you took the sphere, you can't go in a straight line. On a sphere, if you want to go straight, you simply cannot go straight. And why you cannot go straight? Because there are no straight lines. So that's the same thing here. There are no straight lines here. So it has to go in a curve. Of course, this picture is slightly misleading because they have drawn it as a projection in space. And many times students ask this question that, oh, but your field is weak. See, the sun, I mean, some of the students who have already read a little bit ahead, the field is weak near the Earth of the sun. And if the field is weak, should it be close to the space-time of special relativity? Shouldn't it be a straight line, almost a straight line? Why is it curved so much like a ellipse? But the point is, this is in space only. I've taken a projection. If you look, so this is where the speed of light comes in. The Earth moves at a much slower speed than the speed of light. Earth moves at the rate of 30 kilometers per second, which is 10,000 times slower than the speed of light. So if you draw this curve in a space-time diagram, then it will be almost straight. Okay, so there's no problem here. So this is my first part of the thing. So if anybody has questions, they can ask.
Participants, if you have any questions, can you just raise your hand and then we can allow you to speak. Does anyone have any questions? There are no questions at this stage, Sanjeev. I believe you can proceed and we can maybe stop after 30 minutes to
Okay.
see whether
So after that, I think now I'll go up to the end because
okay.
But this was the first part, it was the elementary Einstein's theory. Sorry, I have to just got this cold, so I have to keep on drinking this water to clear my throat. Anyway, okay. So I go to now linearized gravity. Okay. So slightly curved space-times. So G alpha beta. So what we are going to talk of is the propagation of gravitational waves. We start with that. Then we will talk about the generation and so on, and detection also. So first we'll do the linearized Einstein's equations, because we try to simplify them. As I told you, these equations are horribly complicated. But when we are talking of astrophysical gravitational waves, okay, like things from binaries and so on, and you're talking about the propagation away from the source, okay, in the wave zone, for example, then the metric can be simplified. The space-time for such a thing would be the background plus a small perturbation of the background. And for simplicity, I have taken the background to be flat. Eta alpha beta is the Minkowski metric. Okay, so G alpha beta is the metric which I have already come here, shown here. So now you have G alpha beta is eta alpha beta plus H alpha beta. So slightly curved space-times and coordinate system chosen is almost Cartesian. Okay. So this G alpha beta is eta alpha beta plus H alpha beta, and what we assume is that mod of H alpha beta is much less than 1. Okay, so now this thing, I would like to give some idea what this means. This can now apply to the orbit of the Earth also, for example. The H alpha beta, if you look at calculate from, go back and calculate from Einstein's theory, from the Schwarzschild solution, for example, then H naught naught, if you take the G naught naught thing, would be 1 minus 2m over r. Okay. So if it is 1 minus 2m over r, 2m is the Schwarzschild radius. 2m for the sun is just 3 kilometers. Okay. M for the sun is like 10 to the 33 grams. 2 into 10 to the 33 grams. And if you divide that by c square and so on, you will get the Schwarzschild radius with something like 3 kilometers or a little less than that. But the distance of the Earth is something like 150 million kilometers, okay, from the sun. So if you take that, this 2m over r would be of the order of 10 to the minus 8. Okay. So the metric differs even at the Earth from the sun. You take the Schwarzschild geometry and look at the metric near the Earth as calculated from Einstein's theory, it would differ from the flat space by amount like 10 to the minus 8. Okay. So that's what it is. So there's something like 10 to the minus 8. But now we are going to talk of gravitational waves, and those are even weaker. So even if you thought of a binary system which is collapsing, like binary black holes and so on, the first event which was there, I'll talk of it a bit later at the end of my lectures, GW 150914, for example, that produced an edge of something like 10 to the minus 21. 10 to the minus 21 as compared to 1. The eta is 1, minus 1, 1, 1, 1. So I'm fixing the signature of the metric to be this, minus, plus, plus, plus. And so eta will be -1. So if I write it as a matrix, the diagonal components will be -1, +1, +1, +1. So it is H alpha beta is so small. So this is what we have here. Now, so next thing we do is, if we want to talk of propagation of gravitational waves, we try to choose the best possible metric we can, the best possible coordinate system we can, in which we have to do the least amount of algebra. We are basically lazy. We don't want to do too much calculations, or in some way smart, that I mean, to get the same physics, why work more? So in that case, one should choose a good coordinate system. So we are free to choose any coordinate system we want, but the physics is coordinate independent. So there's no problem what coordinate system we use. We will therefore choose this coordinate system as per our convenience. So we will therefore choose that coordinate system which simplifies the calculations and extracts the physics. We do this even in Newtonian physics, as I say, and you can actually try to see what happens, or even in electrodynamics. You keep an off-center charge, say even on some z-axis or something, at a point z equal to a, and try to write the field of this charge in spherical polar coordinate system. You'll get a whole mess of all the spherical harmonics and things like that, or PL cos theta and all that sort of stuff. But you put it at the center, you put the origin at the center, choose the charge, choose the origin so that the charge is at the origin, then it's fine. Then it's just Q over R. And you'll get the field to be even of a static charge very simply. So we do this even in Newtonian physics. This was for electrodynamics or electrostatics. Try to get the potential for point mass in some crazy coordinate system, it will go crazy. So this is what, this is the point of it. So how do we choose this coordinate system? Ask the question, what are the coordinate transformations that will keep mod of H alpha beta much less than 1? So that is the point. See, not all coordinate transformations will keep this small. Okay, so you have to be careful in choosing the coordinate systems. So what are those? So there will be many of them, but we will only take two types of coordinate transformations. So one are background Lorentz transformations. So x prime alpha equal to lambda alpha beta x beta. These are just Lorentz transformations which keep the eta alpha beta the same. So they just make eta, if you just Lorentz transform the eta alpha beta, by this Lorentz transformation you get the same eta alpha beta. So it's invariant under this transformation, you get the same thing back. So these also keep the H alpha beta small, because this is the Lorentz transformations are also quite bounded. The gauge transformations, the others are gauge transformations. The gauge transformations are these: x prime alpha equal to x alpha plus xi alpha, where xi alpha comma beta is much less than 1. So xi alpha, think of xi alpha as the dimensions of length, and if you do take its derivative, comma means partial derivative with respect to beta, then this becomes dimensionless, and you can put this boundary, put this condition. Mod of this is much less than 1. So if you do this kind of thing, you will keep H alpha beta in the new coordinate system also small. So the first one, for example, which is the background Lorentz transformation, G prime alpha beta equal to this lambda mu alpha, lambda nu beta, G mu nu equal to eta mu nu plus lambda mu alpha, lambda nu beta, H alpha beta. This will be equal to, this is still the eta mu nu. I mean, so it is, so eta mu, nothing happens to eta alpha beta. So eta alpha beta becomes just eta mu nu. I mean, you go back to the g mu nu I had written here. So it becomes eta mu nu, but you have these things hitting h alpha beta, and which you write as a new h prime mu nu. So the Lorentz transform h alpha beta is h prime mu nu. So h prime mu nu transforms like a Lorentz tensor. You can see that it is transforming like that. So now this is a fiction. So now you can assume this fiction that h alpha beta is a field on the background of a flat background spacetime. So h alpha, since it transforms like a Lorentz tensor, we can regard h alpha beta as a tensor field defined over a background flat spacetime with metric eta mu nu. Also other fields like h alpha beta, like the Riemann tensor and so on, which are just now, since you are in this kind of thing, all covariant derivatives and all that will become partial derivatives. We are going to do that kind of a thing here. Can be regarded as fields over the background spacetime, flat background spacetime. So now we calculate the Riemann tensor to the first order in h alpha beta. So this is the first part of the thing, that we are going to have these two types of things. This will be called gauge transformations. So actually saying G is a tensor in the big, it's actually what is called tensor in the general coordinate system, or what is called a GLNR group. Okay, if you want to talk in the high sounding way, GLNR general transformation, this thing. It's a GLNR tensor. It's much more this thing there, but you're going to allow these kind of things and look upon these as gauge transformations. So that's another remark which I wanted to make, that we will not look at this as because these are like, there's a background tensor field. So if you regard things on the, look at your space-time as a background Lorentz, what do you call, flat space-time, then this is simply like a Lorentz tensor here. The others are regarded as gauge transformations. Okay, so the Riemann tensor to the first order is here. R alpha beta mu nu can be written like this. Half of, so now you see there are a lot of calculations. So I don't know how to, I'll just go through these calculations. And the thing is that unless you do them yourself, you really don't. I mean, if you are doing this for the first time, you will, you will not get the feeling of it, because many of these calculations will be gone through in the tutorial in the afternoon, I guess, today or tomorrow. So R alpha mu beta nu is simply the first order. So as you know that, as you have seen, it's a non-linear function of G's. If you looked at the metric, the Riemann tensor, there are products of gammas and things like that coming into the picture, and gammas themselves are like this. So yeah. So what have we done here? We are going to raise and lower indices with eta alpha beta. Okay, because we are going to keep only first order terms in h alpha beta. So here is the thing, h alpha beta, we keep first order terms. So h mu nu, comma mu beta. So these are the ones which I have written down here. And the rest of the terms are gamma square terms. That means gamma multiplies gamma. But gamma itself is order of h. So gamma is what? Where is it? Gamma is here. G alpha beta, there is a derivative with respect to this. So G beta delta, for example, the first term is eta beta delta plus H beta delta. Eta beta delta is a constant, so that goes to 0 and becomes H. So gamma becomes order of H. So gamma is extremely small. And when you raise and lower indices, we will raise and lower it because any other term, raising and lowering also, raising means it will be eta alpha beta minus H alpha beta. See the minus there, it's just because it's like a, when you do this rotations or whatever, the inverse of I plus epsilon, if you do infinitesimal rotations in classical mechanics, the inverse of I plus epsilon rotation matrix is I minus epsilon. So it's like that. If you multiply G alpha beta by G alpha beta, you will get identity plus order of H square, which anyway we are not taking into account. So you can check that G alpha beta, G beta gamma is delta alpha gamma. You can always check that plus order of H square. Okay. So we are throwing away that. Since we are throwing away that, this is fine. G alpha beta to be just taken as eta alpha beta. So the Ricci tensor now is you raise it with eta alpha beta. So now you raise this is what happens, this is what you get. Just stare at the equation and you will see it looks something like this. Half of beta mu this thing, you are just raising the indices, okay? So where is the thing? Alpha, the first index is raised up. So that goes up. So look at this expression, the one, I don't know whether you can see my arrow moving across the screen. So look at this and this and so on. Compare these things, raise this index, and what you get is a situation like this. But you must do this for yourself. I think it will be done again in the tutorial, but unless you yourself do it, I think that's what the tutor should do. That they should see that you yourself are doing the calculations. Only then you get the hang of it. You have to do it once at least. Okay. And perhaps once only. Anyway. So define the trace reverse of H mu nu. So this is the kind of thing, eta mu nu minus this. So here you get a better, the Einstein's equations might become better. And it's exactly the kind of arrangement you have in Einstein's equations. Because Einstein's equations are also similar. See there, R mu nu minus half R G mu nu. So you need arrangement to basically something like that. And that's the logic behind this H bar, trace reverse of H. So H mu nu, so here the algebra becomes simple. You define a new quantity. H, so this is also a Lorentz tensor. H mu nu minus half eta mu nu H, where H is the trace of H mu nu. Take the trace and you write it like this. And the Lorentz gauge is given here in, this is now, so now we are going to put the gauge condition. Okay. So the Lorentz gauge, it's called the Lorentz gauge. And this term is borrowed from electrodynamics. There also you have a Lorentz gauge. Say in when you have these field theories, okay, like electrodynamics and so on, when you are doing actually calculations for some charge distributions and so on, it is important to choose, or it is useful to choose a good gauge, okay, in which the calculations are again simplified. For example, if you are doing magnetostatics, then you choose the Coulomb gauge. The divergence of A, the vector potential, what is that? B is del cross A. So divergence of A is 0, then things become simple. But if you are doing waves, for example, electromagnetic waves, then you have divergence of A plus 1 by C, d phi by dt equal to 0. Or in the covariant language, it is A mu comma mu is 0. The divergence of the four potential A mu write as phi and A, that is 0. So in analogy with that, we call this also the Lorentz gauge. It's the name. So H bar mu nu comma nu, you set equal to 0. So the question is, can you set it equal to 0? No, that is what will be argued somewhere, either in the lectures or maybe in the tutorial. Okay. Is it always possible to do this? Okay. So set this equal to 0. So if you suppose we can, and if you can set this equal to 0, things simplify dramatically. So if you set this equal to 0, what you get is H. So now I think I pulled down the mu. And what happens is that you pull the mu down, then this becomes H nu mu comma nu is this. Okay. And now you substitute back into R mu nu and so on. And see what do we get. So then what happens is that these two terms which were there, I think, where are they? Okay. Yeah. These two terms which are there, they just become half of H mu. So these are which? These are the first two terms. In this, in 2.2, if you see, the first two terms come this. First term is equal to the second term equal to half of H comma mu nu. And
Sanjeev, I'm sorry to interrupt. We can see your mouse. So if you can use the mouse to point, it will be helpful.
Okay. You can see my mouse. Okay, great. So this one and this one. Look at these two terms. Each of them, this term becomes equal to this term by this gauge, in this gauge. Okay. So this first term becomes equal to the second term. And that is equal to this. So actually, I think these things you have to work out yourself. It's very rather this thing to explain. And I think it should be done in the tutorial properly. So they become all half of H mu nu. But now if you look at this here, there's a minus of H comma mu nu here. Okay. So these two terms add up to cancel out this term. So the first three terms simply go away. Okay, in this thing. So I have dropped some steps, or I think these things will be done more in detail in the tutorial. Somewhere I have said tutorial, yeah, tutorial for detailed calculation. Okay, so I leave it for the tutorial actually. There are other things which I want to do also, but I think I have progressed quite okay, as I see from my the pages of my lectures. Okay, so H mu nu, is it clear? I mean, Shriram, I mean, or is it again a little bit?
Maybe we can just see whether there are questions, if that is okay with you.
Yeah, sure.
Okay. Participants, if there are any questions, please raise your hand and we can unmute you so that you can ask the question. Is there any question from anyone?
I don't know at what level. I mean, I can't see the participants, so I don't know what the reaction.
I am not able. Yeah, I'm assuming that they will raise their hand and speak up if they have questions. Sanjeev.
Yeah.
Okay. Maybe, or raise your hand. Or you can also leave a message in the chat. We can read out the question for Professor Dhurandhar. Sanjeev, at this stage, there are no questions, so you can proceed with the lecture. And I'm assuming that if there are questions, they will ask towards the end.
Okay. But the only thing I'm wondering whether is this going, I mean, is this too easy or it is too...
No, it is fine, Sanjeev. Maybe you can slightly speed up, but I think we are fine.
Yeah, so this is what it is. So the first three terms cancel out and you get R mu nu equal to this. So this is the first thing you get. R mu nu equal to minus half box of H mu nu. Box is the D'Alembertian operator. Okay. So it is in our what do you call, in the signature, it is just del squared minus 1 minus c squared or d del square minus 1 over c squared d squared dt squared. Okay. Keep the c. So R mu nu is this. And the scalar curvature R is eta mu nu R mu nu. Okay. So now you have to get the scalar curvature. Now, if you go back to the Einstein's equations, what are they? I mean, there is a scalar curvature also which you need. So if you look at the scalar curvature, it is eta mu nu R mu nu, but it is R is equal to this minus half R eta mu nu box H mu nu. Okay. And so, but eta mu nu is a constant, so I can take it inside. Okay, the box. The box is, remember, is just derivatives, which is the D'Alembertian operator. So if you take eta mu nu inside this is, what is eta mu nu H mu nu? It is just a trace of H, which is minus half H. But then now if you combine these two things together, what do you get? This minus this becomes H bar, which we had defined earlier, the barred quantity which we defined here, the trace reverse of H mu nu. Okay. So it is exactly H bar mu nu, which you get here. And so the left-hand side of Einstein's equation, which was a formidable set of G's and so on, becomes simplified so much in this thing just by using the Lorentz gauge. Okay. So we are going to, so our idea is to, given our physical problem of gravitational waves, wait a minute.
Sanjeev, meanwhile, there is a question I notice on the chat. It asks, what is the physical meaning of a gauge transformation and how does one use it?
Physical meaning, I mean, at least at the classical level, I don't think there's any. It's just to simplify calculations. So, physical meaning is the same thing, is that when you go to potentials instead of the fields, there are many ways to choose the potential, and which corresponds to the same field. So in case of electrodynamics, the A and phi is there. You can use many other A's and phi's for getting the same E's and B's. Okay, and you have this choice. So you have this freedom to choose whatever gauge you want, whatever gauge you need, you want, and you choose it in such a way that it simplifies the calculations. That is the whole thing. That's exactly what we are doing here. We are simplifying the calculations, we are saving the labor. Because finally, what is this gauge? It's a coordinate transformation. And since you are doing this kind of thing, coordinate transformations don't change the physics. So the physical meaning is this, that gauge transformations don't change the physics. But they make a big difference to the calculations. Is that?
Okay. Yeah. This was a question on the chat, Sanjeev. I'm reading out, so I presume they will respond on the chat if they are happy with the answer. So the other question,
basically for mathematical convenience, I mean, the thing is that you can, I mean, they don't change the physics, but they change the mathematics or the algebra rather. Okay, and so you use them in a smart way to reduce your algebra or make your calculation simple. That's the whole idea. So use it in a smart way. So because you use this thing here, exploit the gauge freedom. And this is exactly what we have done here to simplify the Einstein's equations, given this astrophysical situation where the waves are weak, say coming from binary black holes or whatever. Okay, things like that, where h is like 10 to the minus 21, 22 or something like that.
Yeah, the student says that he understands. The other question is that do we take the trace of h mu nu with respect to the metric? What do we take the trace with respect to?
Eta mu nu.
Okay, I understand.
Okay.
So there is another question. The student has raised his hand. Akash, can you unmute and speak?
Yeah.
Go ahead and ask your question. Unmute and speak, Akash.
Can you hear me now?
Yeah.
Yes, we can.
Yeah. So my question is, you described the background Lorentz transformation. So you said that under background Lorentz transformations, the new h prime that you will get, it will be also much less than 1. So my question is, can there not exist Lorentz transformations for which these gamma alpha betas can become very high? So suppose I go to a frame which has a very high velocity, and then its gamma factor will be very large, tending to infinity.
So the high velocity is just V or C in that. See, there's a C there.
No. But say in the gamma factor definition, 1 by 1 under square root 1 minus v square by c square, that factor can potentially grow to infinity, right?
So his concern is that gamma may, raise these to very large values. That is the concern.
Yeah.
The H alpha beta, you mean?
That is correct. Under the transformation, it will pick up a gamma. Can't gamma be large? This is concern.
Right. That's a good question, actually. So, yeah, I suppose so. But anyway, I think the point of this whole thing was to show that this is, we can regard it as a background field. That was the point of this argument, actually. So we are not going to use it anywhere.
Okay. Can I ask one more question?
Yeah.
Just very briefly, Akash, we can have further questions towards the end of the ask a brief question.
We are actually going to use the gauge transformations.
Okay.
Go ahead, Akash.
Yeah. So my question is that in the calculation of the weak field Riemann tensor, you said that the gamma will be of order h.
Yeah.
H square. Yeah.
Order h, right?
Order h, yeah.
Yes.
Order h. But in the definition of gamma, I guess you are saying that because of the presence of first derivatives of G alpha beta.
Right?
Yeah, but we never said that the derivatives of H alpha beta are small. We just said that that the H alpha beta itself is small.
Yeah, so there the thing you have to look at what you are taking derivatives. So it's like the wavelength comes in, basically. See, in a gravitational wave, when you take the derivative, it is I omega t and so on. So one has to compare terms there actually in this case. So in case of h, it is dimensionless. But when you take this, you have to compare lengths actually.
Oh, okay. Got it. Thanks.
Yeah, so that's so the factor k comes. So you will see it, and when I go to the next thing. So then it is when you use the gauge transformations, the k comes on both sides. What is the wave number?
Okay.
And it just cancels out.
Okay. Thank you, Akash, for your question. Sanjeev, I think you can proceed and we can take more questions towards the end of the lecture.
So wherever, here. Okay. So I have basically at the end of this. So this is the thing. R was equal to minus half of box of H, and R mu nu minus half eta mu nu R is minus half box of H bar mu nu. So is this so let me get back to this. So first of all, we had this H mu nu, which cancels out. R mu nu is minus half box H mu nu, And other thing which I want to say is that many of the students here, I mean, they should actually do these calculations. It's very important to do this calculation so that you yourself experience it. Like when you do the Schwarzschild solution, you actually, at least I tell them, if I teach, MSc or whatever, final year MSc students, I take something like a 3-hour class, okay, for doing the Schwarzschild solution. 3 hours with a break of half an hour in between. So during that half an hour, many of the students run away, but that is no problem. So, but thing is that I do the Schwarzschild solution in one go. R00, R01, R11, all these things have to be calculated. And you write them in now terms of nu and lambda and so on. So I always tell them that you must do this once, at least, in order that you get an idea of how complicated the Einstein's equations are, what all is involved. The same thing is here actually. There, of course, I tell them do it once and do it only once. Don't do it again. Okay. So, but you must do it at least once. So this is the thing here. So it is minus half box h, then r mu nu minus half eta mu nu r, then is equal to, because then you combine all these two equations together to get exactly that, because half of h mu nu minus this half of this. So it will give you minus half h bar mu nu. So the Einstein's equations are this. So this is the climax of all this thing, that now we have got an equation which is linear. Okay, that's the point. Now we've got an equation which is linear. You can superpose solutions and all that sort of thing. There's no problem with this thing. You can superpose gravitational waves, okay, if they are weak. So here we have this box of h bar mu nu equal to minus 16 pi g by C4 T mu nu. So the factor of 2 goes away on the other side. And if you want, I think in tutorial, these calculations will be done perhaps more in detail, and there you might ask questions. So the next thing is choosing the gauge freedom. Okay. So right now we have chosen. We have said that we can choose such a gauge, that h bar mu nu comma nu is 0. Okay. How do you know you can choose such a gauge? Okay. So there is a gauge freedom. So choosing the Lorentz gauge. So now x prime mu nu, x mu is xi mu. Where xi mu is small. So such that xi mu comma nu is much less than 1. So you now have to calculate this kind of derivatives, partial derivatives which come in tensors, because you're going to do this. You want to calculate what happens to, what you want to get is finally h bar comma mu nu in the new coordinate system. Okay. So what we want to prove or show is that you can, that there is, so we actually what we are doing is we are trying to understand the gauge freedom. What can we do with this gauge freedom? How free we are to choose the coordinates. And once we know that answer to that question, we will be able to exploit that freedom in order to make our calculations as simple as possible. And finally, we'll arrive at what is called the transverse traceless gauge. And so there are 8 components of h mu nu, and this is where we are heading. We will have 8 conditions which we will impose on the h mu nu, and finally what we will have is just 2 independent degrees of freedom, which will be the 2 polarizations of the gravitational waves. So in general relativity, what you have is gravitational waves have 2 degrees of polarization. In fact, if you have seen, this theory starts resembling Maxwell's theory. In fact, this equation itself, which you see here, just like Maxwell's equations, box of a mu equal to 4 pi by c j mu. So you remember your electrodynamics. The a mu is the 4 potential or the vector potential, and j mu is the 4 current. Then you have box a mu is 4 pi by c j mu, and this thing in fact exactly resembles that. So x prime mu is this, xi mu is small, and you have this here. So Shriram, I just wanted to know how much time do you have? So hello.
You have about 15 minutes, Sanjeev.
That includes questions.
No. We can. You can stop. We can take a few more minutes of questions beyond 15 minutes too.
I see. No, I mean, I can stop almost any time.
Okay, maybe you can go on for some more time, and I will. You can go for another 9 minutes or so, and then we can take questions, Sanjeev.
Okay. So here is the thing: x prime mu equal to x mu plus xi mu. So xi mu is small, then in the sense that this is less than 1. Okay. So you have this to take the partial derivatives, you get this kind of quantities, you get this kind of quantities. Now you check that these are actually inverses of each other. So here is this, and here is the inverse of this. Remember, this is the inverse is with a minus sign. It's like I plus epsilon, inverse is I minus epsilon, where you have matrices. You are taking a matrix like, say, A equal to I is the identity matrix plus a small matrix, say epsilon. Then A inverse is what? I minus epsilon. Because if you multiply I plus epsilon into I minus epsilon, the linear term will cancel in epsilon. What you'll get order of epsilon square. So to the level of accuracy, you are still fine. So delta mu alpha, delta mu psi mu comma alpha, this equal to delta mu nu plus this minus this plus order of xi square. So this last 2 terms out of that which we neglect, and therefore it is the inverse. Okay? Delta xi mu nu. So this is what we'll use. So now, how do you calculate h prime mu nu? You have to go back to the original metric, because remember that we have just pretended that we have a field over a background space time. Okay, actually you are in the full 4-dimensional space time with the metric g mu nu. So that you must always remember that there at the back of the mind. We are doing all this just to simplify calculations and make our life simple. So g prime mu nu is this. This you multiply here. So this multiplies this, and what you get is eta alpha beta, h alpha beta. You have to multiply these 3 terms, and what you get is the first, this thing will hit alpha, h alpha beta. This term hits h alpha beta. You get h mu nu, and minus this kind of thing here, delta. I mean, you have to, this is what the second term here, first term here, and eta alpha beta. And then what happens here? I think the eta beta mu, where is that? This term and that term, yeah. First term of the first bracket, second term of the second bracket, and the third term there. That is this over here. Okay. Yeah, I probably forgot the eta mu nu here. But anyway, I think that should be put there. Yeah, there's an error in this second line, but there must be an eta mu nu there. Okay. Yeah. But the rest of them are higher order terms. But then this is equal to eta mu nu plus what you call h prime mu nu. Okay. So this gives to the first order of smallness h prime mu nu equal to h mu nu minus I mu comma nu minus I nu comma mu. Okay. So this is what comes out if you have this. So this is how it transforms under the gauge transformations. Remember, this is like a background field, and we are making a gauge transformation which looks like this. So again, I have written the same equation. H prime mu nu is equal to h mu nu and zeta mu comma nu, zeta nu comma mu. Then this then h prime is equal to eta mu nu is equal, so what we are doing, so we need to calculate h bar. Okay, so we are going back to this thing. This we want in the term after gauge transformation. What happens to h bar mu nu? And finally, you will take its divergence. So I hope you can see where we are leading to. So h prime mu nu is this, h prime is this, and so h prime is just raise it with eta mu nu. So this becomes h minus 2 xi mu comma nu. From these, we must compute h bar mu nu, which is now h prime mu nu minus half h eta mu nu. So this is what, so you have got these two pieces together. Now you put these two pieces together to calculate h bar mu nu. So this is what it goes to. Maybe I'll stop here. I don't know what to do, or
Maybe you can complete this discussion.
okay, let's me see. Right. So this gives the first order in smallness. This, yeah, okay. So this is what you need to do this here. So h bar prime mu nu is this. So you put all these things together. Okay. So when you put them all together, this is what you get. H mu nu minus psi nu, this thing. So all these calculations, actually you will have to do this. And again, I guess in the tutorial it should be done. Half h this. You can follow this calculation. So this is, so this term and that term will give you h bar. And then these two terms just come down here. And this term gives you eta alpha, eta mu nu, psi alpha comma psi alpha. So this is the new h prime mu nu after the gauge transformation. Now you need to take the divergence. So now you take the divergence of this quantity. So the divergence is, so raise all indices and then take the divergence with respect to nu. So you get h mu nu comma nu, h xi mu nu comma nu, and plus this in square brackets I put xi nu comma mu plus eta mu nu, this term, okay, which has come out here. But the point is that these two terms are the same except for the minus sign. Xi mu comma nu and eta mu nu, because you can raise this index with eta mu. You can take the eta mu nu inside because it's a constant. So raise it so that you will get to the mu. Okay. So you raise that index, and what you will get is exactly this term. So the terms in the square brackets will cancel out, and what you get is finally h bar mu nu comma nu equal to minus box of xi mu equal to 0. So then we must solve this equation. Okay, this is non-zero. So this we started with the original equation. So this could be non-zero. You may not have started with the Lorentz gauge. You may have started with anything. You have just used some coordinate system to calculate your h mu nu, which is useful. So this all often happens with the source. You might have some source, astrophysical source, and then you are calculating using some quadrupole formula or whatever, okay, the h mu nu, and the thing is that may not be in the Lorentz gauge at all, okay. So h mu nu, this may not be equal to 0. So in which case, you can go to h prime mu nu. This is what it's telling you, okay. We must solve this equation. If you solve this and get xi mu, so you have to show that xi mu exists, that's all. To get xi mu, and hence the Lorentz gauge, okay. And these are just partial differential equations, and given boundary conditions and regularity conditions, solutions always exist. This is from the theory of partial differential equations. So if you have reasonable boundary conditions and regularity conditions, then you are solving an inhomogeneous equation for a D'Alembertian operator, and in which case solutions always exist. Therefore, xi mu exists, and we have the Lorentz gauge. So that's the basic thing over here. And so this, as I said here, so this you get to the Lorentz gauge, but it is not really a gauge, one gauge. However, the gauge is not fixed because we can add xi mu to zeta mu to xi mu, where box of xi mu is 0. So you can always add zeta mu to this here without changing this equation. So these xi mu's are actually a family of gauges, which are the Lorentz. So Lorentz gauge is not a fixed gauge. It is a family of gauges. And doing this does not fix the gauge. But we will fix the gauge later on, because that makes our life even more simple. Okay, let's stop here.
Thank you very much, Sanjeev. I noticed there is a raised hand already. Daniel, unmute and speak. Ask your question.
Sir, can you hear me?
Yes.
Yes, we can.
Okay, so can you please move to page number 16? Thank you, sir. So the second set of equations, the second and third equation, this is the partial differentiation of the first equations with respect to x alpha and x bar mu. But my question is, the last equation you have given here, by the differentiation, it should be equal, right? It should be equal to delta mu alpha minus psi alpha comma mu. Why is it approximately equal or nearly equal?
It should come from that equation, because that x mu is not. See, this equation has not followed from the first equation. Okay. It is followed from the fact that you are taking. I am taking the inverse of this equation.
Okay. Are there any extra terms after this?
And this is, you can see that x alpha also, I mean, could follow, I guess, because there's the inverse relation.
Yes.
And it's not exact, of course.
Okay.
So there is order of xi square.
Okay, sir.
That I have not written down there. Perhaps I should write. But that's why I have written approximately.
Okay, sir. Thank you, sir.
Thanks, Daniel, for your question. Are there any other questions? Please raise your hand or leave a message in the chat box as is convenient for you. Okay.
I would
One
like.
last time.
I
Yeah.
don't
Go ahead, Sanjeev.
have idea of who my audience is. So it was like I was going blind. So into this thing. So I don't know exactly who I'm addressing. So do the participants already know all this? Then it will be very, or they are really.
So many of them are graduate students, and there are a few master students, but all of them have been exposed to some elements or adequate elements of general relativity.
Okay.
And they may have been exposed to some elements of gravitational waves as well. But there may be a few master students who had limited exposure to. Chandra, am I correct in this regard?
Yes.
Yeah.
So, I mean, I don't know at what level. I mean, I can pitch the lectures at any level, but I thought I'll pitch is this the right level to pitch it? That's what I was asking.
I believe it is largely fine, Sanjeev. Maybe, you can ensure that, you can set up a speech so that you can cover what you had hoped to.
I'm properly covering up. I mean,
okay.
Here, I've done a reasonably, I think I've done 1/3 the job.
Okay, very good. So there is another question. Samik, unmute and ask your question. Samik, go ahead. You have to unmute, Samik. We have given you permission to unmute. Please unmute and ask your question. Samik, let me say one more time. Just unmute and ask the question, Samik. Okay, Samik seems to have some difficulty. Maybe you can leave a question in the chat.
Yeah, that you can
chat. Yeah. Are there any other questions?
Let him write
okay.
That, then you can ask me.
Yeah. Samik, we may close soon, so you can leave a message and then or ask Professor Dhurandhar at the start of the next lecture.
Yeah,
whichever way is fine. Yeah,
that also is fine.
Yeah, I don't see any further questions, Sanjeev. So I think we can stop here for now.
Yeah.
Thank you very much, Sanjeev, for your first lecture.